I titled this video Solid, Liquids, and Intermolecular Forces, or this set of chapters. That's not the title of either chapter, but those are the three major topics we're going to be focusing on in this set of chapters. The first one we're actually going to focus on is intermolecular forces. It just kind of made better sense to put it at the end. So intramolecular forces are the forces that we learned about when we were talking about bonds. Those are the connections literally between atoms that make a molecule. Intermolecular forces are the forces that are found between molecules rather than the intra forces. And these impact what state you find your substance in. The stronger the forces, these intermolecular forces are, the more likely you are to find it in a solid or liquid state at room temperature. The weaker these forces are, the more likely you are to find it in a gaseous state. Solids and liquids are considered to be condensed states because they have a set volume, a definite volume, and gases, however, will take the volume of whatever container they're found in. So intermolecular forces will affect your melting point and boiling point because those connections have to be broken in order for the substance to change forms. We know that a solid state is more condensed, whereas a liquid state there's a little bit more free-flowing nature, whereas in a gaseous state the molecules are spread very far throughout. This will also affect how things dissolve in one another, which is why you don't see oil and water dissolving in one another very readily. But these forces have to be overcome as well, and the energy that's provided by the temperature of the molecules or from another source is going to determine whether these forces can be broken or not. So there's four main forces we're going to focus on: electrostatic, dipole-dipole, hydrogen bonds, London dispersion. Electrostatic is also known as ionic, and that's going to be the first one we're going to talk about. These are formed between oppositely charged ions. So we're going to see these solely with our ionic compounds, and this is what causes salt and other types of ionic compounds, nitrates, acetates, chlorides, to have really high melting points and boiling points. These are going to be the strongest forces that have to be overcome, which is why you are not ever going to be able to make salt melt on your stove at home. The next force we're going to talk about is dipole-dipole. And dipole-dipole is probably second from the bottom on the totem pole. We find these with polar molecules. And what happens is that in your polar molecules you have a positive end and a negative end. And the negative end of one polar molecule will line up with the polar end of another dipole-dipole molecule or another polar molecule, and that causes there to kind of be this magnetic attraction towards each other. We find these a lot in liquids. Now keep in mind with these forces, and even with the electrostatic forces, these are not nearly as strong as the intramolecular forces. Dipole-dipole is about 1%. Electrostatic might be 4 to 5%. And as your atoms get larger and you're spreading out further, you don't have as strong of a force, which is why you won't have to deal with these as much once you have turned a liquid completely over into a gas. So this is just kind of an example. We've got here our negative and positive ends of our molecules, and we see how the positive ends are being drawn towards the negative and vice versa. Okay, the red lines are going to be where we see attraction, so we see positives and negatives. And then we have some green lines in here as well, and those are the ones that are going to try to push us away as far as possible. So we really want to line them up so that the positives and negatives are closer together than two positives or two negatives. This is the strongest of the non-ionic forces, the hydrogen bonds. These are found in polar molecules that contain nitrogen, oxygen, or fluorine, as well as a hydrogen atom. And what will happen is that hydrogens will, or the fluorine, nitrogen, and oxygen, which are all extremely electronegative, will reach out for the hydrogen atom on an adjacent molecule and again form an attraction. And molecules that contain these, this is going to be their strongest intermolecular force. So this is a type of dipole-dipole force. but hydrogen bonds are a special type, which is why water is able to act as such a wonderful universal solvent, because it is extremely polar due to the hydrogen bonds that are formed between each of the hydrogen atoms and an adjacent oxygen. We also see this with like hydrogen peroxide, ammonia, and hydrogen fluoride. The dipole-dipole forces we talked about previously are also present in molecules that exhibit hydrogen bonding, but hydrogen bonding is the dominant intermolecular force. So here we see water, we see the negative oxygen atom of the water molecules reaching out for the positive hydrogens and increasing that attraction between them to cause them to form and not a true network, but kind of an invisible connection that has to be broken for water to change from ice to water, or more specifically when water changes from a liquid to a gas. The last one, London dispersion forces, is actually present in everything. And as long as any of the other forces are present, this one will not be the dominant force. We see this with our nonpolar molecules, so like gasoline, and our noble gases, our diatomic gases. What happens in these molecules is that each of these atoms has both protons and electrons, and the more electrons that are present, sometimes one side of the molecule will have a little bit more of a negative charge on it than the other. And when that happens, we have a little bit of asymmetry, and so the molecule becomes instantaneously polar for just a brief little bit of time, and it causes an adjacent molecule to also become asymmetrically polar. The more electrons you have, the more likely this force is to be seen. It's going to tend to be a little bit stronger. And so if you go down the row with the halogens, fluorine's a gas. We see that chlorine is also a gas. Bromine is a liquid, whereas iodine is a solid. And as we go down, we are increasing our electrons, which is increasing our polarizability because we have more electrons in iodine than we did in bromine or chlorine or fluorine. And so we see that iodine is more willing to keep its state as a solid at room temperature, whereas bromine is not as likely to be found as a gas at room temperature because of that increased number of electrons and these intermolecular forces that have to be overcome before iodine can become a liquid or bromine can become a gas. Fluorine and chlorine do not have as high of a polarizability as the other two, and so they are found as gases at room temperature. So here's a couple of examples of London dispersion forces. In the one on the left, we have atoms. We see here that the electrons are pretty much evenly distributed, and now all of a sudden on atom A we have more of the red dots on the left side, so it's more we have more of a negative side to that atom and more of a positive side to our right one. And then if we look at atom B, that's going to cause atom B to become instantaneously polar, because this positive side of atom A is going to attract more electrons from atom B over to that side. Maybe a little bit easier to see with the molecules here. We see that they're both pink, and now all of a sudden we see more of a reddish side to the negative component of molecule A, and more of a whitish, pinkish, a light pinkish side to molecule A, its positive end. And as that instantaneous dipole forms, it pushes molecule B to also form an instantaneous dipole. So again, in order of strength, we have our electrostatic forces, which we find in our ionic compounds. We have our hydrogen bonds, which are found in any polar molecule that contains nitrogen, oxygen, fluorine, as well as a hydrogen atom. We have dipole-dipole forces, which are found in our polar molecules. And then we have London dispersion forces, which are found in pretty much everything. So 3 factors that influence intermolecular strength. I just talked about the first one. The length of the chain will also influence the strength. If you have a longer set of atoms, whether they be carbons, we're going to have more forces be involved, because there's going to be a greater number of places where those intermolecular forces can contribute within molecules. Whereas with smaller atoms, you don't have as many places for intermolecular forces. Some are stronger than others, but if you're comparing methanol to, let's say, octanol, octanol's got a longer chain of carbons, and you're going to see more of the forces represent themselves in octanol, which would have 8 carbons attached to an OH, as opposed to methanol with 1 carbon and an OH. And again, the size, we've talked about that with the halogens, and the same thing would apply with the noble gases. The larger your molecule, you're going to see more of those London dispersion forces dominate, and you're going to see stronger intermolecular forces as a result. So in this particular example, I'm asking you to identify, and this will be for all the ones in this video, we're going to look at what is the most important type or types of intermolecular forces that's present in the solid form of these substances. So we're going to need to be able to identify what our substances are, whether they're polar or nonpolar, whether they're ionic or not ionic, and use that to determine where they fall in the chain. So NH4Cl is an ionic compound, so we already know right away all ionics, their strongest force is going to be the electrostatic forces. We will also see dipole-dipole forces because all ionic compounds by definition are polar. We will not see hydrogen bonding because we do not have hydrogen atoms. That NH4 is an ion. We don't see hydrogen atoms in this molecule. That NH4 is a charged group of atoms and ion. Here we have polyethylene, which is a series of carbon atoms connected to 2 methyl groups, CH3. So it's just a straight long chain of carbons. That N is just representing any amount of carbons you want to have. Polyethylene is used in plastics. We are not an ionic compound, so electrostatic forces do not apply. Nitrogen, oxygen, fluorine atoms are not present, so hydrogen bonding does not apply. This molecule has symmetry. It's made of just carbons and hydrogens, so dipole-dipole forces won't apply. So the only force that truly applies in this molecule will be London dispersion forces. And we will have more of these London dispersion forces depending on how large that N value is. In this compound we have chloroform, CHCl3. We have carbon in the center, the 3 chlorines are on the outside, as well as the hydrogen. This molecule will be polar because we will have asymmetry with the 3 chlorine atoms pulling the electrons towards that side of the molecule and the hydrogen side being partially positive. It is not ionic, so dipole-dipole forces are going to play a role. We will not have hydrogen bonding because there is no nitrogen, oxygen, or fluorine atom. And London dispersion forces would be in play for a small extent, but dipole-dipole forces are going to be the dominant force. Finally, we have NH3. So nitrogen is bonded to the 3 hydrogen atoms with a lone pair of electrons on the nitrogen atom. This is not ionic. We don't have a metal-nonmetal ion combination, but we do have hydrogen bonding occurring because the nitrogen and hydrogen is attached directly to one another. And so the nitrogen's lone pair can reach out for an adjacent hydrogen atom on another ammonia molecule. Dipole-dipole forces would be in play a little bit as well as London dispersion forces slightly, but the hydrogen bonding is going to be the dominant. This is the end of this particular video, and then in our next one we're going to look at some properties of substances that are impacted by these intermolecular forces.